Hi everyone, welcome to this presentation. My name is Victor Cabrera. I'm a professor at the National Polytechnic Institute in Mexico. And first, I'd like to thank the organizers for the opportunity to participate in this conference. NUSOT is a great forum to present our theoretical work about organic solar cells. And today, I'll be presenting our approach to analyze the built-in electric field in irregular morphologies of bulk-heterojunction solar cells. But before starting, I want to thank my student, Giancarlos Flores, and my colleague, Luis Martin Resendiz, who have collaborated in this topic with me. To begin the discussion, I will start with the definition of the problem. What is a bulk-heterojunction solar cell, and how are they modulated? In the second part, I'm going to talk about the computational details, and then the simulation results will be presented and discussed. At the end, some conclusion will be given. Solar cells in general have a semiconductor between two electrodes, anode and cathode, where the solar energy or sunlight is converted into electrical energy. Organic photovoltaic cells are a type of solar cells that use organic semiconductor instead of traditional materials such as silicon in the active layer. These devices have been attractive because they have potential to be very cheap, lightweight, and mechanically flexible. Despite these advantages, organic solar cells don't yet have the efficiency required to compete with inorganic solar cells. In order to improve their performance, it is necessary to understand how they work. In the active layer of these devices, there is an heterojunction to create an electric field at the interface between two types of organic semiconductors, an electron-donating material and electron-accepting material, so that when a photon is absorbed in the active layer, an exciton is created. If the exciton is created close enough to the donor-acceptor interface, the exciton can be dissociated by the electric field into charge carrier and contribute to photocurrent. One of the disadvantages of organic semiconductor materials is that they have short exciton diffusion length, so only the exciton generated around the interface can be dissociated into free charge carriers. Then, an organic solar cell with a bilayer structure like this exhibit low power conversion efficiency because the small interface into the active layer. To overcome exciton dissociation problems in organic solar cells, the bulk heterojunction architecture has been used. In this structure, the interface is distributed throughout the volume of the active layer, and a more effective charge separation is achieved. The ideal morphology for the active layer is the interdigitated heterojunction structure, where vertically aligned donor nanopillars are surrounded by acceptor materials with nanoscale phase separation or vice versa. However, the implementation of the ideal interdigitated structure is difficult. Instead, a mixed solution deposition method is the most extensively used because it's not expensive and high power conversion efficiency can be achieved. In this case, active layers with irregular morphologies, something like this, are obtained since the random mixing nature of the donor and acceptor during solution processing. So a typical organic solar cell looks like this with an irregular morphology, which is not easy to analyze and model. One of the models that have been used to describe the active layer of organic solar cells is the model proposed by Koster, which is known as metal insulator metal model or mean model that consists in obtaining an effective medium from the characteristic of the two semiconductors, the donor and acceptor material. The energy difference between the LUMO energy of the acceptor and the HOMO energy level of the donor function as the band gap of the semiconductor, of the effective medium. When this model is used, a thermal equilibrium energy band diagram like this is obtained. As we can see, an electric field that separates the exciton is generated throughout the active layer. This simple model has been very useful to understand many aspects of organic solar cells. Many experimental results have been explained. However, there are other aspects that this model cannot describe, such as the morphology properties of the active layer. So instead, we propose a model that takes into account the properties of the morphology. So in our work, we use an algorithm to generate irregular morphologies in 2 dimensions. In the first step, the algorithm creates its points that are randomly dispersed in the active layer. The number of these points controls the domain size of the morphology. Then a random number between 0 and 1 is generated and compared with a threshold value to decide which material is each point. With this threshold value, the weight ratio of the morphology can be controlled. And finally, each point grows radially outward until it finds the domain from another point. Here we can see an animation that shows how the algorithm works. The first sample has 100 nucleation points, while the second one has 1000 nucleation points. Both have 1-to-1 donor-acceptor ratio. The result is that with less nucleation points, the domain size is large, while with more points, the domain size is small. In the last 2 samples, the weight ratio was changed to show how the morphology are modified. The electrical modeling of organic solar cells is based on 3 coupled differential equations, Poisson's equation, and the continuity equation for the electron and hole current densities. The system is complemented by equations which represent the drift and diffusion current densities. In the literature, the recombination in organic semiconductors have been extensively studied with different proposals. Here, the recombination rate was modeled considering bimolecular recombination with a direct recombination constant. The current densities were defined with the Maxwell-Boltzmann distribution. Generation rate is a function of position and represents the absorption of sunlight in the active layer. However, for simplicity, we take it as constant. The full system was solved in 2 dimensions and considered a steady state. To validate our method, we considered an effective medium and the parameters of the semiconductor reported in this reference. The potential and the electric field that are shown in this plot were calculated under short circuit condition. The red and the blue colors represent the maximum and the minimum. As we can see in this plot, the electric field is concentrated at the electrodes. To observe it better, in the figure below, a cross-section of the electric field is plotted. The density current voltage characteristic was obtained also, and the electrical parameters such as the short circuit current density, the open circuit voltage, and the fill factor were compared with the values reported in the reference to validate our methodology. In this work, we were interested in simulating irregular morphologies but we also simulated regular morphologies to use them as references. Two irregular morphologies with different domain sizes were considered, and the transport parameters of the semiconductors were taken from the same reference as those used in the validation, but the energy levels of the donor and acceptor materials were arbitrarily proposed as shown in the energy band diagram. In this slide, the results of the bilayer structure are shown, despite the fact that the bilayer structure that we simulate is not an effective medium, it is an heterojunction. The results showed that with this model, the electric field is higher near the contacts instead of at the interface. To modify this behavior, we propose adding impurities to the semiconductors. When the doping increases, the electric field begins to concentrate mainly at the interface. The current voltage characteristic of the most doped sample presents the worst performance, which is in agreement with what is expected of a bilayer structure. The interdigitated structure was simulated under different conditions. In this case, changing the height of the fingers. As expected, the best performance was obtained with the 18 nanometer sample because in this sample the electric field is distributed throughout the active layer. Once our approach was validated with regular morphologies, it was applied to samples with irregular morphologies. As can be seen, the maximum of the electric field is observed at the domain boundary. If we analyze the electrical parameters of these solar cells, we can realize that the maximum power is obtained with larger domains. To understand why the morphology with the largest domain size is better, the potential is shown in the following graphs. When the domain size is large, the carriers can find pathways without potential barriers to the electrodes. And when the average domain size is small, there is a lack of continuous pathways that affects the transport of electron holes towards the corresponding electrodes. By comparing all the results, it can be seen that the worst cell is the one with the bilayer structure, and the best is the one with the interdigitated structure, while the performance of the cells with irregular morphologies is between these two. These results, we can say that the approach proposed here can be used to describe the phenomena that takes place in the active layer of an organic solar cells in a better way than a model that considers an effective medium only. In summary, I want to emphasize that with the method that I have presented here, it is possible to analyze irregular morphologies taking into account the electric field that is created at the interface of the heterojunction in the volume of the active layers. The behavior of the results is in agreement with the experimental results that had been reported in the literature. We also show that in this approach, the heterojunction parameters can be considered with the diffusion model, and a donor and acceptor doping is used to modulate the electric field created at the interface. And finally, although we have chosen arbitrary semiconductor materials to illustrate our approach, the conclusions are general and should apply to any heterojunction. Okay, this is now the end of my talk. Thank you very much for your attention for this research. And please feel free to submit any question for me to answer during the conference. En Spanish, muchas gracias. Adiós.